Hello, good evening. I am Mahesh Hegde. I am working as mathematics lecturer. So, in this session, we are going to discuss a small concept, a subtopic of the chapter matrices and determinants. So, we are going to see some properties of adjoint in this session. So, adjoint of a matrix is a very important concept if you are a student who is preparing for any competitive exam after your 12th board exams, such as JEE Mains or KCET or MHTCET or APCET. Any such exams, you can expect questions from this chapter and also from this concept itself. So, when I say adjoint of a matrix, we all know how to find adjoint of a matrix. So, if I have a matrix a 3 cross 3 matrix, when we say adjoint, we are discussing only the square matrices. So we can talk about adjoint for only square matrices. So if I have a matrix a 3 cross 3 matrix, let's say A11, A12, A13, A21, A22, A23, A31, A32, A33. Here Aij are the entries of the matrix. A is the matrix. So it is a 3 cross 3 matrix. Now, for this particular matrix, for this A matrix, I can find the cofactor matrix. Let me define it as, or let me denote it as CA, cofactor matrix of this particular matrix A, and it can be written as C11, C12, C13, C21, C22, C23, C31, C32, C33. Cofactor matrix is again 3 cross 3 matrix. The cofactor matrix that I have defined here, it is nothing but the matrix formed from the matrix A, the matrix formed from the matrix original matrix A, where each entry of this cofactor matrix is the cofactor of the corresponding entry from the matrix. Meaning, if I take the C11 entry, it is nothing but cofactor of cofactor of A11 entry from the original A matrix. In general, Cij entry is nothing but cofactor of the entry Aij. So, using this property, we can find the cofactor matrix for the given matrix A. Now, adjoint of a matrix is defined as adjoint of a matrix is defined as adjoint of A is equal to the transpose of the cofactor matrix. So very simple definition for adjoint of a matrix. So adjoint of A is transpose of the cofactor matrix. So for this particular matrix, CA is already known, cofactor matrix is already known. To write the adjoint, I have to take the transpose of the already known CA matrix or cofactor matrix. So our adjoint for the A matrix will be adjoint of A will be C11. Transpose means shifting or interchanging rows with columns. So C11, C12, first row becomes first column, C13, C21, C22, C23, C31, C32, C33. This will be our adjoint matrix. So this is our adjoint matrix. Once adjoint of a matrix is known, next we are going to see some of the properties regarding the adjoint of a matrix. So we are going to start with the first and very important property. First one is A into adjoint of A is equal to adjoint of A into A is equal to determinant of A into I. Very, very important property regarding adjoints. We can prove this. Let me take a simple 3 cross 3 matrix. A matrix is A11, A12, A13, A21, A22, A23, A31, A32, A33. So I have a 3 cross 3 matrix. If I write the adjoint of this particular matrix, adjoint of A, it will be C11, C12, C13, C21, C22, C33, C23, C31, C32, C33. So this is the adjoint of the matrix. Now I have to multiply this A matrix with adjoint matrix, meaning I'll get a 3 cross 3 matrix again. The order of A matrix is 3 cross 3, order of adjoint is 3 cross 3. So the matrix multiplication of A and adjoint of A, that is A into adjoint of A, is again a matrix of order 3 cross 3, order 3 cross 3, in which entries will be given by. Observe here, for the first entry, we can observe A11 entry for A into adjoint of A. This entry will be given by multiplying first row of A matrix with first column of adjoint of A matrix. We can see A11 gets multiplied with C11 plus A12 gets multiplied with C12 plus A13 gets multiplied with C13, which will give us the result determinant of A. Can you recall the result? A11 C11 plus A12 C12 plus A13 C13. This is nothing but the multiplication of rows of a matrix with corresponding entries of cofactors. So this will give us determinant of A. So using this property, first entry of A into adjoint of A will be determinant of A. Similarly, if I look at the second entry of A into adjoint of A, second entry, for second entry I have to multiply the first row of A matrix with second column of adjoint of A matrix, meaning A11 into C21 plus A12 into C22 plus A13 into C23. We can clearly observe the elements of first row are getting multiplied with cofactors of second row, which will give us the answer 0. Similarly, for 1 3 entry, I have to multiply first row with the third column of adjoint of A, which will again give us answer 0. Continuing like this, second row multiplied with first column will give us answer 0. Second row with second column A21 C21 plus A22 C22 plus A23 C23. This will give us answer adjoint determinant of A. Similarly, next A21 C31 plus A22 C32 plus A23 C33. This will give us 0, and again 0 0 determinant of A. This is clearly visible. Therefore, if I observe the matrix again, here I can take determinant of A common, determinant of A common. The remaining matrix is 1 0 0 0 1 0 0 0 1. This new matrix is nothing but the identity matrix of order 3. So this can be written as determinant of A into I. Therefore, we have a very important result, very important result. A into adjoint of A is equal to adjoint of A into A, which is equal to determinant of A into I. Determinant of A into I. So we have one very important result proved. Now, moving on to the second result. Second result, we have second result is determinant of adjoint of A. What will be the value of determinant of adjoint of A? This we need to calculate for the second result. Observe here, we already have a result A into adjoint of A is equal to adjoint of A into A is equal to determinant of A into I. So, if I use that result, A into adjoint of A is equal to determinant of A into I. This result I am using. Now what we can do is we can take determinant on both sides. If we take determinant on both sides, we'll have determinant of A into adjoint of A is equal to determinant of A into I. We have this situation now. Now we can recall some of the results from determinants. Which are the required results? One result is one result is determinant of AB, multiplication of two matrix, then taking the determinant. It is determinant of A into determinant of B. This is one important result. Next, determinant of K into A, where K is a random constant, a variable, sorry, a constant. K is a constant, A is a matrix. So determinant of Ka is K power n into determinant of A. When a constant comes out of the determinant, it gets raised to the power of the order of the given matrix. So K power n into determinant of A, n is order of the matrix. So this is the result we are going to use here. We have A into adjoint of A inside determinant is equal to determinant of A into I. So using first result, determinant of AB is equal to determinant of A into determinant of B. I can write the left hand side as determinant of A into determinant of adjoint of A. This is equal to, we can see in the right hand side, determinant of A will be a constant. When a constant comes out of the determinant, it gets raised to the power of the order of the matrix. So this result will be determinant of A power n, where n is the order of the matrix, into determinant of I. So this result we have applied. Now observe, we require determinant of adjoint of A. Assuming that determinant of A is non-zero, that is A is non-singular. A is non-singular. We are assuming this result. What we can do is we can divide the whole equation by determinant of A, so that we'll get the result. Determinant of adjoint of A is equal to determinant of A power n into determinant of identity matrix. We all know it is equal to 1 divided by determinant of A. Hence, we are going to get the result. Determinant of adjoint of A is equal to determinant of A power n minus 1. So, determinant of adjoint of A is equal to determinant of A power n minus 1. One very important result. I'm going to highlight this. Second result, determinant of adjoint of A is equal to determinant of A power n minus 1. So this was our very important second result. Now, moving on to the next result, we have the third thing we are going to derive is adjoint of A. What will be this answer? We are going to see in a minute. Adjoint of A matrix. Again, very important result we are going to use is the first one, A into adjoint of A, or to avoid confusion, I can take x into adjoint of x is equal to determinant of x into I. This result we are going to use again. Here, adjoint of, inside the adjoint, we have again adjoint of A, right? So, we can pre-multiply with adjoint of A matrix to the original equation to get adjoint of A into adjoint of A. What will be this result? I can treat adjoint of A as X matrix, then adjoint of X is written. So X into adjoint of X is written. It is determinant of X into I. That is determinant of adjoint of A into identity matrix. So adjoint of A into adjoint of A is it is determinant of adjoint of A into identity matrix. Again, I don't want this adjoint of A on the left hand side. So to get rid of it, I can pre-multiply the whole equation with A matrix, so that the new equation becomes A into adjoint of A into adjoint of A is equal to, we know the result, determinant of adjoint of A. It is determinant of A power n minus 1 into, I have pre-multiplied with A, so A into identity matrix. Now again one more beautiful result, A into adjoint of A is determinant of A into I multiplied with adjoint of A is equal to determinant of A power n minus 1. A into identity matrix is A. Again we require this adjoint of A. So I can divide throughout by determinant of A, assuming that determinant of A is non-zero. Assuming determinant of A is non-zero, I can divide throughout by determinant of A. I gets multiplied with this matrix will give the original matrix itself. So the required result, adjoint of A is equal to determinant of A power n minus 1 into A matrix divided by determinant of A. Hence, the answer we are going to get is, therefore, adjoint of A is equal to determinant of A power n minus 2 into A. So, adjoint of A is equal to determinant of A power n minus 2 into A. So, the third result that we have seen is adjoint of A is equal to determinant of A power n minus 2 into A. Moving on to the next result, the fourth one, we have already seen adjoint of A is equal to determinant of A power n minus 2. Now, what we are going to see is, if we take determinant here, determinant of adjoint of A, what will be this result? We are going to observe that. Look here, we already have the result, adjoint of A. It is determinant of A power n minus 2 into A. Now I need determinant of adjoint of A. That's why I'll take determinant on both sides. It implies that determinant of adjoint of A is equal to, right hand side also determinant, it is determinant of A power n minus 2 into A. Again, determinant of A power n minus 2 is a constant. Constant coming out of the determinant gets raised to the power of order. So, determinant of A power n minus 2 gets raised to power n, where n is the order of the matrix, into determinant of A. If you simplify this, we'll get left hand side is determinant of adjoint of A, it is equal to determinant of A power n minus 2 power n, it is n square minus 2n into determinant of A is there, so power gets added with 1. So determinant of n square minus 2n plus 1, this expression is nothing but determinant of A power n minus 1 the whole square. So the fourth result precisely we have seen is determinant of adjoint of A. It is determinant of A power n minus 1 the whole square. We can extend the result, or we can generalize this result to any number of matrices, meaning if I take determinant of adjoint of A, it will be determinant of A power n minus 1 the whole cube. Similarly, if I take one more adjoint, determinant of adjoint of adjoint of A, it will be determinant of A power n minus 1 whole power 4. We can continue like this. So this was our fourth result. This was our fourth result. Next one, again, very, very important result. The fifth one, adjoint of adjoint of Ka matrix. Adjoint of Ka matrix K is K is a constant. Adjoint of Ka. What will be this result? Adjoint of Ka matrix. So again, I am going to use the property. First property, x into adjoint of A, x into adjoint of X matrix, x into adjoint of X matrix is equal to determinant of X matrix into X. X into adjoint of X is equal to determinant of X into X matrix. So I am going to use this result again. We have adjoint of Ka. So to use this result, I'll pre-multiply with Ka matrix. So I have Ka matrix into adjoint of Ka matrix. It is determinant of Ka matrix into, so one mistake I have committed. So x into adjoint of x is determinant of x into identity matrix. So here also Ka into adjoint of Ka is determinant of Ka into identity matrix. So if you observe the right hand side, Ka matrix is there and its determinant, it is k power n into determinant of A into identity matrix. Here on the left hand side, we have Ka into adjoint of Ka matrix. I can cancel out k on both the sides. So on the right hand side, k power n minus 1 remains. On the left hand side, I have a into adjoint of ka is equal to k power n minus 1, a constant, into determinant of a constant, into identity matrix. Now I want adjoint of ka, so I have to get rid of this a on the left hand side. To get rid of a, again I have to pre-multiply by adjoint of a matrix. So if I pre-multiply with adjoint of a on both sides, so adjoint of a into a matrix into adjoint of ka matrix, it is k power n minus 1 is a constant, determinant of a is a constant. I have pre-multiplied with adjoint of a into identity matrix. Now again we can observe adjoint of a into a. Adjoint of a into a is very well known result. Determinant of a into I into adjoint of ka is equal to k power n minus 1 into determinant of a into adjoint of a. Here determinant of a is on both sides. Assuming that it is non-zero, I can cancel out I into adjoint of a. So we are arriving at the required result. Adjoint of ka is equal to k power n minus 1 into adjoint of a. So the fifth very, very important result, adjoint of Ka matrix, it is equal to k power n minus 1 into adjoint of A matrix. So these were the five very important results. One more result, it is very commonly you might have observed, not in adjoint frequently, but in other cases. When I write the result, you'll get idea of it. The result is adjoint of A into B matrix. Adjoint of A into B matrix, it is adjoint of B matrix into adjoint of A matrix. We might have seen these results. AB the whole transpose. AB the whole transpose is B transpose into A transpose. AB the whole inverse. It is equal to B inverse into A inverse. We call these results as reversal laws for transpose, reversal law for inverse. The same reversal law will also hold for adjoints also. That means adjoint of A into B matrix will be adjoint of B into adjoint of A matrix. So this final result we are going to prove. We have adjoint of AB matrix. So I'll multiply with AB matrix on the left hand side. AB into adjoint of AB matrix. So the answer will be determinant of A into B into identity matrix. So I need adjoint of AB. So again I'll pre-multiply with adjoint of AB on both sides. Adjoint of AB matrix, adjoint of AB matrix into AB matrix into adjoint of AB. It is equal to determinant of A into determinant of B. I have pre-multiplied with adjoint of. So as we can observe, AB into adjoint of AB is equal to determinant of AB into identity matrix. So I'll pre-multiply with adjoint of A first, so that I'll have adjoint of A into A matrix. I can club these two into B matrix into adjoint of AB matrix. This will be determinant of A into determinant of B. I have pre-multiplied with adjoint of A into identity matrix. Now, adjoint of A into A is determinant of A into identity matrix. Remaining terms are B into adjoint of AB matrix. It is equal to determinant of A, determinant of B, adjoint of A into I is adjoint of A. Assuming determinant of A is non-zero, we can cancel that out. Remaining terms are B into adjoint of AB is equal to determinant of B into adjoint of A. So again I have to get rid of B to get the required result. So again what I can do is I can pre-multiply with adjoint of B on both sides. So adjoint of B into B matrix into adjoint of AB matrix. It is equal to determinant of B is a constant. We have pre-multiplied with adjoint of B into adjoint of A. Again, adjoint of B into B, it is nothing but determinant of B into identity matrix into adjoint of AB matrix. It is equal to determinant of B into adjoint of B into adjoint of. We can cancel out the determinant of B also, assuming determinant of B is also non-zero. So we have the sixth important result. We can call it as reversal law for adjoints. The sixth result is adjoint of AB is equal to adjoint of B into adjoint of A. So these are the six important results that we have observed in this session. I'm going to write these things down one last time so that you can remember. The first result was the basic, the property of adjoint was adjoint of was defined as adjoint of A was the transpose of the cofactor matrix. This was the very basic thing about adjoint. Next, we had started seeing the results. The first result was A into adjoint of A is equal to adjoint of A into A is equal to determinant of A into identity matrix. This was the first result. The second result was determinant of adjoint of A. Determinant of adjoint of A was determinant of A power n minus 1, where n is the order of the matrix. Whatever result we have seen, the n quantity that represents the order of the matrix. So determinant of adjoint of A is determinant of A power n minus 1. The third result was adjoint of A. It is equal to determinant of A power n minus 2 into A matrix. This is adjoint of A. And the fourth result was determinant of adjoint of A. It is equal to determinant of A power n minus 1 the whole square into, yes, determinant of A is equal to determinant of A power n minus 1 the whole square. Similarly, we can extend it to many cases, n number of cases, determinant of adjoint and so on. The power gets raised. Determinant of A power n minus 1, its power gets raised accordingly with the adjoints. So the fifth result was adjoint of Ka adjoint of Ka is equal to K power n minus 1 into adjoint of AB. And the sixth result, the reversal law, it was adjoint of AB matrix, it is equal to adjoint of B matrix into adjoint of A matrix. So these were the six important results that we have seen in this session. Thank you for watching. Happy preparation. Thank you all.